if we have eigenvalue and an eigenvector, then just by plugging in an element of the spin group, you immediately can see that all other values which are on a certain sphere, basically what you define here is nothing else than a sphere by a point, and then you rotate around. And that basically means that right eigenvalues are in fact spheres. So of course you can always take a representative, but you have this part. It also means another thing, that the right eigenvalue problem is nonlinear. You cannot take out constants to the right anymore, since there your lambda is residing. Another thing which you can also simply see on that part is actually the definition of a determinant. I mean, everybody would simply look, okay, quaternionic matrix or Clifford-valued matrix, let's define a determinant. And if you look at it in the literature, you find literally dozens of different definitions. That's not surprising, because basically what usually is happening, persons pick up all the definitions, all the properties, and use that one as a definition. Problem is, in this case, it doesn't work like that, because most of the definitions, like for instance, if you use permutations or so, don't really work in that case. That's why it's actually rather interesting to look at these things in these cases, because if you really want to understand linear algebra, in these cases, you actually realize what is important. And for instance, if you want to define the determinant, then the real important property is the Schur complement, which you basically see here. And that means basically that you can define the determinant, or should in fact define the determinant via the Schur complement. So forget all the dozens of definitions you have. If you want the Clifford-algebra-valued matrix, the determinant, which does what the classic determinant should do, then you have to define it via Schur complement, which is hereditary. So you can just define it by 2 by 2 and then iterate, no problem there. And also that goes back then to the ideas of Gelfand and so on. But it gives you a feeling that not everything works in the same way as you would expect the classic case. And these things basically come here into play. So, by the way, for the quaternions, of course, there's one thing with the Schur complement. If you just take your matrix and you write it as a real quaternion matrix and just write it as a real matrix and take the determinant of that, that is still equivalent. But if you go, for instance, for Clifford-algebra-valued matrices, it's not anymore. Then it's different. So, but that means basically that we actually have to look for a spectral theory for these operators. And if we do that one, the first thing would be the naive approach, basically, would be to say, okay, let's use a direct approach. I mean, there are other definitions in the past, how to define spectrals of operators, usually based on operators like the Dirac operator and so on, and use that one as a basis to build your spectral theory. But if you want to go via resolvent, then there's a problem. You could simply take the naive approach and just go straight for the resolvent, but there are a couple of things appearing. One thing is basically, that's a nonlinear operator. So you actually don't, instead of a linear problem, you have a nonlinear one to study. And the second problem, that's basically what I write here. There's no connection with the geometric series. And one of the fundamental things in the classic spectral theory is basically, which comes, or you can simply see it as a coincidence or actually coming from the structure, is basically that the summation of the geometric series is also the Cauchy kernel. That's why you have that basically all that connection between classic function theory and spectral theory, that it works together as exactly that point, that the Cauchy kernel basically is also the sum of the geometric series, and the geometric series is what you want to have. So if you look a little bit into the literature, you can find the spectral theorem, spectral theorems going as far back as Oskar Teichmüller in 1936. But this is basically just the decompositions of the operator, so no real notion of spectrum is there involved. And there are several ideas. I'm not going to discuss all that one, etc. I'm pretty sure Fabrizio will do that one in his talk on Friday. The way out, and basically what is nowadays being mainly used, is a notion of the S spectrum by Fabrizio Colombo and Irene Sabadini. And the basic idea behind is at the same time looks natural. On the other hand, it's also not so easy to actually think about it. I mean, there's these kind of Columbian ideas. And the notion they built is actually around the second order scalar operator. I mean, who works in non-commutative structures, usually scalar operators are the easiest ones to handle because then you can commute and everything. But it's not so easy to see that one. And the basic idea below is, or the first idea below, you can simply see if you make that simple calculations. Of course, if you look at it, you will simply see that this one works for S as a complex number. But if you look at it, this term on the right-hand side also makes sense if S is, for instance, a quaternion. Of course, the calculations like that doesn't work anymore, and you don't have commutations. But on the right-hand side, you have Q here, basically as the only one which is really quaternionic, and S basically, even if you use a quaternion, it would still be the real part and the modulus. So that's the part. You also, if you look a little bit near to it, see that that this one basically, if you know complex analysis, is denominator of the Poisson kernel. So we actually see also the Laplacian lurking behind that one. But the principal thing is that this part is basically working with S for a general thing. And additionally, you have the connection with the geometric series in that case, that you actually have exactly the first formula here. You could also simply switch Q and S. That just would mean that the last term goes to the front. But you can basically see from that part that you now have actually a geometric series and a kernel on the right-hand side and the series on the left-hand side for, well, developing spectral theory. And then we can use the following definition that we just take T from the Banach algebra of bounded operators, and we define the S resolvent Z, basically asking that this denominator here is basically invertible. So, and of course, the spectrum is then defined as the complementary set of all these operators. And this operator we call the pseudo-resolvent. If you now look at it, this is of course a nice idea. It basically reduces the discussion of an operator where S basically is separated into real part and the modulus, which also makes sense because if you think about it, eigenvalues are spheres. So a certain rotational symmetry you would like to have. But one thing you can simply see if you compare that one to the one on top, to the geometric series, you will simply see, well, we have only one part of it, but not the other. Of course, for the definition, that part here doesn't play a role. For the invertibility, that's completely irrelevant. On the other hand, for the series, to get the series, that is essential. So one needs a little bit more than just pseudo-resolvent operator. And that's basically why you have to also work with the left and right resolvent operator. So left and right resolvent operators, the Q is nothing else than what you see above here. So that's the denominator which defines invertibility, but then you multiply it from one side or the other. You have the left and the right resolvent operator, and you could, a priori, if you're just interested in, let's say, working with initially just with a Cauchy integral formula or things like that, then the left or the right resolvent operator would be good enough. On the other hand, if you look for the resolvent equation, let me just recall, in the classic one, you would have basically the resolvent operator, would be just a minus I minus 1, a minus mu I minus 1. Then, of course, we all know the classic resolvent. That's a minus lambda I times a minus mu I, both with the minus 1. So both resolvent times lambda minus mu. So that's an essential part. And if you want to have the same thing here, resolvent, then you will see that there is no way you can get that one just with one of them, either the left or the right. So our problem now is basically, how can we get that part? And for that one, you can see we need both of them. So when we work with them, you cannot simply say, I only use a left resolvent or a right resolvent. You need to use both if you want to work. that's basically something we should keep in mind. Okay, then one of the things, another thing which I'm going to use here, I don't know if you're how far familiar you are with that one. Probably in the classic case, most of you are, I mean, that's classic operator theory, are familiar with that. But anyway, I want to actually just recall it also for the case of the quaternionic operators, this triangular representation if you have a finite rank operator, so matrix. Then of course, we can always decompose T into D plus V, where D is diagonal, V is nilpotent. Also in the quaternionic case, there's nothing changing here against the classic one. And if you give me an orthonormal basis, then I can write my operator like this. EJ is the orthogonal projector onto the subspace generated by EJ. Usually you want then the eigenspaces, of course. And of course, you have the separation with the parts, and that means you can introduce the projectors, which is nothing else than projecting to the subspaces by adding always one. And that means T can be decomposed by this. And of course, it's relatively easy to see that this one would be D, this one would be V. Yeah, and I mean, in classic linear algebra, first year semester, you would simply say if V, in fact, the nilpotent part is 0, then the matrix is diagonalizable. So nothing on that particularly. But we are here interested in the quaternionic case. This part basically goes through like that. But how does it work in the general case? So, well, for that one, we introduce eigenchains. Who is familiar with it basically can just keep it. The other ones, think of that part that you take a set of autoprojectors and consider as a chain. If in any pair inside our things, you can decide which one is bigger. So bigger actually, which image is contained in the other. We call the chain bordered if 0 or I belong to P. And if you have a pair of operators inside that chain, then of course you call a gap any pair for which there's nothing in between. That's basically what we're actually saying here. So when you say this part here, then basically we say only there's nothing in between, so it's a gap there. And the chain is maximal if you cannot be enlarged, so that whatever you actually want to add, it's not anymore going to be. The classic thing, of course, is a resolution of the identity. And in particularly, we say that the chain is an eigenchain of the operator if all the ranges of the spaces are invariant. So basically invariant subspaces. So basically think of it as eigenspaces of the operator. So one of the things we need is basically our change to the nilpotent operators, and that of course are, if you especially looked in, if you are familiar with the work of Livsic, Brodskii, and all these Russian school of Gohberg and Krein and so on, are Volterra operators. So in our context, we just take a quaternionic Hilbert module and a bounded left or right linear operator, whose spectrum only contains 0. Then we call it a Volterra operator. And the characterization is basically the same, like you can do also in the classic case, that if you have a maximal eigenchain of your operator, then for every gap we have, that T applied to the gap is 0. This is basically also the classic characterization, and this continues to be true in the quaternionic case. Now, the integration of a quaternionic chain is also relatively straightforward. You basically, when I define that one and say it's defined in the usual way, basically it's defined as a Riemann sum. So you basically take your chain P, you write it as a sum, and then basically you just fill it up, depending on if it's discrete, then of course all the integral becomes the sum. If it's continuous, then of course we have our integral. One of the things which comes already from if you just look at it, discrete one, is that the necessary for convergence is that on every gap, the whole thing disappears. I mean, otherwise the integral wouldn't converge. If you want to check it, just write a special case where it's a sum and then infinite sum, and then you have. And now there's one special thing you have to keep in mind. in the Quaternionic case is about the imaginary part. We define the imaginary part t minus t star here. Of course, for a Quaternionic one, that means basically just the vector part. So if I do that one, and you have t given like t0 plus I, t1 plus k, t3, then of course this part would be just the vector part. If you go for Clifford-valued operators, then of course it's a little bit more. It's not just the vector part. And it actually depends a little bit what you have because of the conjugation, etc. So it's also not simply that you just would isolate the scalar part, because it depends if you're trivectors, bivectors, trivectors, and so on, where the conjugation gives you the same element in the basis of the basis and which ones are not. So, but if we introduce that one, then we can particularly get the following formula, that we can get our operator back by integrating over the projected imaginary part. So these ones actually contains the principal information for that. Now, one of the things we are interested here is non-selfadjoint operators. And that means, first of all, we should look at p-triangular representations. So let's simply take an operator's maximal resolution of the identity, bounded or unbounded. And we assume that we actually have a decomposition like in the case of the finite ring operator. So T can be written into a normal operator plus a Volterra operator. And this part basically means that the resolution of the identity is compatible with these operators. Then I call T a pre-triangular operators. Pre-triangular in the sense that he actually has a triangular decomposition. So in case of matrices, basically you can think of a Volterra operator as an upper or lower matrix with zeros on the diagonal. D as a diagonal operator, so that gives you the idea where the name comes from. So D and P are called the diagonal representation, and exactly in that form. So what we can now do with p-triangular operators in the Quaternionic case? Well, first of all, and now comes the interesting part. First of all, T and V are bounded operators, well, having the same maximal eigenchain. And V is a Volterra operator. Then TV, so the composition of these operators continue to be Volterra operators with the same eigenchain. That's important for us because basically one of the key points in what we are doing afterwards is that lemma. That's one of the key lemmas, because basically says if T is a possibly unbounded p-triangle operator, then we want to work with our pseudo resolvent operators, in this case with respect to the diagonal. And for that one, we need to work with them, we need V applied to them. And here we can simply state that they continue to be Volterra operators and they have the same maximal eigenchain, so that they don't change out. That's important because you will see in a minute that the formulas, there's one thing with these Qs, etc. Since we actually work with second order formulas, the classic tricks of decomposing the operator, when you actually have that part, so that you have A minus lambda I appearing somewhere, and then you basically, for instance, A you write as D plus V, and then you put D in evidence and so on, do not work here so simple. So one of the things which is the same as in the classic case, that's also what you have in the classic case, is basically that the S spectrum of the operator, so the spectrum basically is totally contained in the diagonal part of T. So it's also straightforward coming from the nilpotent part basically has only zero. Another tool which we need, of course, is when we talk about that one, operators, isolating compact operators, that means we need to introduce Schatten-von Neumann class. There's a problem which is already in the Quaternionic case, the same problem like you would have in all non-commutative structures or even in non-commutative geometry and so on. If you want a trace operator, then the first problem you have is you cannot define it like in the classic case. I mean, normally what you do is if you find a trace operator, you introduce an orthonormal basis, then you make the expansion in terms of the orthonormal basis with respect to the inner products, and that gives you the trace operator. And then afterwards you prove that it's independent of the ortho-chosen basis. That doesn't work here. You cannot simply do that one in that way. That's actually generally, typically a result that you have that one which is valid in the commutative case, but in the non-commutative case, it goes immediately by the drain. So on the other hand, we still have the singular values, especially if T is a compact operator, then T star T, of course, is also eigenvalues and so on. And we have just the standard things. And to introduce the Schatten classes, we take basically a compact operator, T, and we want, of course, that's in LP. That's usually what you expect from the Schatten classes. Usually P equals to 1 are the trace class operators, P equal to 2 is the Hilbert-Schmid operators, and P equal to infinity would be all compact operators. But here, you additionally have one condition, appearing. So, which is basically coming from the fact that, in fact, your singular values, well, or your eigenvalues of the operators are spheres. And in a certain sense, you can simply see that one as basically choosing the representative on your sphere. So you have a sphere, and J basically fixes you, in some sense, what representative you choose. There is an alternative which you could also do. I mean, we are a non-commutative, so you could simply suggest, okay, why not simply going for disk smear trace? We could simply do that one. You could take the disk smear trace. The only thing you have to do is then you have to introduce the Makaev's classes, but that is per se not a problem. And you could build it up from there too. Nothing wrong with that. Can be done. Only that, well, that this part basically might be a little bit more direct the way we do it here and more intuitive from the structure itself, that you actually come from the quaternionic structure instead of using a little bit more bigger cannons. In any case, the norm you have down here, and that's what we need for our classes. So, and since we have that part, we can now actually simply start thinking how to do it now. I mean, for that one, you can go to Brodskii or to actually the Branges and look for spectral decomposition. And the idea is basically behind that one is, of course, we have a bounded operator, and we want that the imaginary part is in one of the Schatten classes. So, and if that one is, then we can simply prove that there exists a maximal orthogonal combination, well, a resolution of the identity and a non-decreasing real functions, H, so that T can be decomposed in such a way. And particularly, this part basically would be then what we actually have, the diagonal part. And if it's unbounded with T and T star, basically you get then the whole thing, but then the integration goes between minus infinity and infinity. I'm not going to speak much about the proofs, otherwise I would simply fill up the next hour. Simply think about it as you can adapt the proofs of the Branges for this case, of course, using slice hypermorphic functions instead of holomorphic functions. You have to be only a little bit careful if you go to his papers there, because proof of the Branges usually have holes. So you better be sure that there are what one is doing there, but the proofs in itself are really adaptations of that part. But it's a little bit more technical. That's why I didn't want to actually say much about that. The only thing important for us is here that you actually have these spectral decompositions in this way, because that's basically what we are using. Now, to get estimates for the pseudo-resolvent, and that's one of the things we want to do, we can choose now a sequence such that it goes fast enough to 0. That's basically necessary. And that the norms of the powers are basically bounded by that, where y is basically in a normed ideal in that part. So think of it as for instance, a Schatten class or something like that. We will actually, in the case of Schatten class, you will see you can even be a little bit more concrete. And now the thing is basically, and here comes a big difference to the classic case. In the classic case, you would basically just simply say, so classic, not our case. You could simply say, okay, look, guys, I write the whole thing as d plus v plus lambda I inverse, and then I put d outside as the inverse, so d minus 1, blah, blah, blah. And you would basically use that decomposition to actually discuss the things, and then d minus 1 is applied to v, and here appears also. And it's rather simple. The problem is we cannot do that here because we do not have the simple form of the resolvent. We have the pseudo resolvent QS, and the decomposition is not that simple. In fact, what you can use is that decomposition here. While it is an infinite, it looks like you can use that one. It looks like an infinite sum, but keep in mind that we already had that the operator inside here is a Volterra operator. That basically is why we have the lemma. So after a certain power, that thing is 0. So while it's formally an infinite sum, in reality, it's a finite sum. But we can simply use this part. And if you use that one, then we can use that decomposition, take then the norms, put the parts, estimate, and you get basically a result like this. Nu S is basically the nilpotency part of the part which I underlined here, there, because that's basically what you need there, where it stops. Otherwise, you can also write it until infinity. And of course, QS, the norm of QS, you can basically connect with the distance of your value S from the spectrum. This one we can actually then simply also do a little bit better. If we, for instance, take now S from one of our Schatten classes, our operator, then we can simply denote the nilpotent part, and then you basically can write it as such, in such a way, T. It's actually basically the same thing as before, just using a small trick, which I wrote down here, which probably, well, I don't know if you're aware of that, but these small tricks are usually what one learns in the first years at university to use. So I don't want to say too much about it, but basically you have the series in the front. The important part here is basically that these zetas I had here before, the zeta k, that zeta k basically I can basically use as 1 over square root of k factorial in this case. And zeta k to the power of p would be then k over p. And you have here basically modulus and that part here, where you actually take the entire part of k over p and take the thing on that. And that's basically where everything comes here into play. So that allows us to get now the following theorem about a triangular representation, that if you have T as a generally unbounded quasi-Hermitian operator, of course, the usual standard thing is that the domain of T and T star is the same. And we additionally impose that the difference, the imaginary part, is a Hilbert-Schmid operator. Then we can simply say that T admits a triangular representation, and the norm of the nilpotent part, the Hilbert-Schmid norm of the nilpotent part, is basically given by that term down here. So the theorem you can also extend to operators to other cases, like for instance, you take operators f of t, where f is slice holomorphic, then you could use the functional calculus. You could also use quasi-unitary operators, so where t star t minus identity would be in one of the Schatten classes, or even operators which are not normal, but let's say have slight perturbation. So almost normal operator where the difference is also in a Schatten class. This is basically for us the question of self-adjoint operators or non-self-adjoint operators. Now, we have the triangular representations. Now, let's look at non-selfadjoint operators. And for that one, I will simply look at the following setting. We take again a maximum resolution of the identity. We decompose our operators T with T and two Volterra operators, which satisfies these conditions. Basically, if you want a simple example, basically think of a finite T as a finite rank operator, then D would be the diagonal, V plus would be the upper triangular part, and V minus the lower triangular part. So that you can basically to have an idea what is behind that one. Of course, D is in this case here is normal, and you have Volterra operators, and they can be a little bit more, but from the classic point of view, if you want to have a slight idea, think of that part. And additionally, we also, again, assume that we have basically a sequence of numbers which fall fast enough to zero here, such that we have such an estimate with respect to a certain ideal. Usually, of course, in practice, one of the Schatten classes, or Makayev classes, if you prefer that one, etc. Now we can simply look at the classic part and simply ask ourselves, well, how far we can replicate it. Now for the invertibility, one could simply say the following. If I take just that the spectrum of the diagonal part is bounded away from zero, V I can define like this, nu of V the nilpotency indices, etc. And then I can simply say that if that part here, one of will be, of course, bigger, but both will be less than one. We have then under the conditions, we can simply say our T is boundedly invertible, and the bound for the inverse is given by that. That's no problem. I can simply just here, the proof in itself is actually basically the same as you would do in the classic case. There's nothing here really which is particularly important for the from the case point of view that we are here in the Quaternionic case. In the case of a Clifford-algebra-valued operators, there's only one thing you would be careful. There would be here still some constants appearing below here. That's the only thing, but that's basically because in the Clifford case, if you have two operators, the modulus of the composition is not less or equal to the modulus of one and the modulus of the other, or only special cases, but you still have a certain constants are 2 to the power n over 2, which actually would basically plug in here. But that would be basically just changing the constants and fixing it, but not really changing the theory by itself. Let's just make the estimates a little bit, let me say, weaker. As a corollary, basically, that's again the same thing. If I now take the concrete case of a Schatten class, Schatten P class, then we basically get the same thing here again, like this. And I could also simply then go one step farther and give the whole thing again for the Schatten classes in these. As I said, this is basically following just the standard case. So here, nothing really, I mean, the proofs are not really bringing anything or requiring anything from the non. The problem now is that in the classic case, you would use that one now to get estimates for the resolvent. Basically, and it's kind of straightforward how that one would work, because basically you would just plug in A as your operator A minus lambda I, and then the inverse of that one would be basically the resolvent, and you could just work with that. Problem for us is we don't have that nice of a possibility. Simply substituting the pseudo-resolvent doesn't work like that. So we have to use a different way. And now comes again the problem with the S resolvents, that in our case, these invertibility rules are not really useful for estimating the resolvent. We have to make a decomposition, and the decomposition which we have to use is basically what I wrote here. Looks a little bit more complicated, and actually, I just saw that I have here a problem. This is basically this part. These parts are actually all the anti-commutators between D and V plus here. And this is V plus, V minus, and also here, D and V minus, basically here, they come. So, and we have to work with that one, and we have to estimate that guy, which makes now the formulas look a little bit ugly. But basically, and that's basically why I actually talked about beforehand, we don't have to reinvent the wheel right now here. We did that one before when we looked here at the at these estimates for the pseudo-resolvent in the first case. Then now in the second case is basically we can use, after using that decomposition, the same ideas. And that leads us to the following theorems. They look more scary than they are, but take the right nilpotency indices, then you can simply estimate it by this. In fact, you can easily notice that this block and this block here is the same, just with B plus and B minus changed. This is basically the same thing you have up here in these ones, because you always can switch them. And you always have to see which ones is the bigger one. So that's why I actually wrote it, but you basically have 2 times the same thing, just with switched. So, and that one I can also put simply to then for the Schatten class again, then it looks like this, distance, etc., and all the things inside. I made one mistake here in the class. These ones are not existing anymore because they are basically coming here. They are already in the constants, which I put there. And with that one, you basically have now the parts, and we could now extend that one to also other cases like what it be before, but it would work in that way. I didn't found a much better way to do that. If somebody has a better idea, one can actually estimate these, basically connect these pseudo-solvents with other operators to make it a little bit more simpler. I would be very much interested, but here I really actually see only the direct way for that. In any case, you can, this one you can estimate by these, with these operators. So in the end, let me give some references. Basically, the first one is basically just the book about all of that one. Brodskii, of course, that's basically where the ideas also for the triangular and so on coming. Well, then the other papers are there. I also put the one of Colombo, Gardner, and Kimsey. And you also have basically the ones, the classic ones, of course, of Gohberg and Krein, where you can find the classic theories and also the theory of non-selfadjoint operators and so on. So thank you for your attention.
Thank you so much, Uwe, for a great talk. Let's thank our speaker. Okay. So are there any questions from the online audience? Any questions from the in-class audience? Okay. Well, Uwe, that's what happens when you give a talk that's too clear, apparently, and nobody has any idea on how to help you with the last slides. So at the moment, there are no questions. So thank you so very much. Let's thank our speaker yet again. And